Somewhere between 2011 and 2015, a spacecraft the size of a small car circled the closest planet to the Sun and quietly photographed nearly 100,000 images of a world everyone had already given up on. Nobody expected those pictures to matter again. NASA's Messenger mission ended its life the way most orbiters do, crashing into the very surface it had spent 4 years studying, and the data went into an archive, where it sat, mostly untouched, for over a decade. Then, in January 2026, a small team of scientists pulled that archive back out, ran it through machine learning models nobody had access to in 2015, and found something hiding in plain sight the entire time. 402 bright streaks cutting down the slopes of craters across Mercury, in patterns too consistent to be random. And the moment those patterns became visible, the story of Mercury as a dead, frozen, unchanging rock started to fall apart. This is the discovery everyone is now calling what NASA found on Mercury. Even though, to be precise about it, the breakthrough came from an independent research group analyzing NASA's old spacecraft data, rather than from a new NASA mission itself. That distinction matters for accuracy, but it barely changes the size of the story. The data belongs to NASA. The spacecraft belongs to NASA. The images that made this possible came from a probe that NASA built, launched, and flew into the Sun's gravity well at enormous cost and risk. What changed in 2026 wasn't the planet. What changed was our ability to finally see what was already there. Let's back up and understand why this planet was ever written off in the first place. Because that context is what makes the new findings hit so hard. Mercury is small, it's barely bigger than Earth's own moon, and for a long time that alone was reason enough to assume it had nothing left to offer. Small planets cool down fast. A cooling planet stops being geologically active fairly quickly in cosmic terms, because the internal heat that drives volcanism, tectonic movement, and crustal change simply runs out. Earth stays warm and active because it's large enough to hold onto its internal heat for billions of years. Mars, smaller than Earth but still sizable, cooled down and largely shut off its geologic engine a few billion years ago, leaving behind frozen volcanoes and dry riverbeds as fossils of a more active past. Mercury, tinier still and sitting right next to a star that bakes its surface at over 400 degrees Celsius during the day, seemed like the ultimate example of a planet that finished its story early and just sat there afterward, absorbing impact after impact with nothing to erase the scars. That's the picture NASA's Mariner 10 spacecraft painted back in the 1970s, during 3 brief flybys that gave humanity its first real look at Mercury's cratered face. And it's largely the picture Messenger reinforced when it became the first spacecraft to actually orbit the planet, starting in 2011. Messenger did find real surprises during its mission, confirmed water ice tucked into permanently shadowed craters near the poles, evidence of ancient volcanic plains, hints of a bizarre and an unusually massive iron core that makes up something like 85% of the planet's radius. But the overall impression that stuck in public memory was simple. Mercury is old, Mercury is dry, Mercury is done. A relic. A fossil planet, a world you study to understand the early solar system, not one you study to understand anything happening today. That reputation held for roughly a decade after Messenger's mission ended, and then a Swiss-based planetary scientist named Valentin Bickel, working out of the Center for Space and Habitability at the University of Bern, decided to take a second look at features nobody had bothered to catalog properly the first time around. The features are called lineae, and if you're picturing something dramatic like glowing lava rivers or towering volcanic plumes, dial that back. Lineae are streaks, bright, narrow linear marks that run down the slopes of craters, similar in basic appearance to features already documented on Mars and on Europa, one of Jupiter's icy moons. A handful of these streaks had actually been noticed on Mercury before, first mentioned at a scientific conference back in 2019, but nobody had gone through and systematically counted them, mapped where they cluster, or tried to understand what caused them. It was the kind of subtle feature that's easy to miss individually and easy to dismiss collectively, especially in a 100,000 image archive that no human team could realistically comb through by eye. That's exactly the kind of problem machine learning is built to solve. Bickel's team trained models to sift through the entire Messenger image catalog, hunting specifically for these bright linear streaks, and the result was the first true census of the phenomenon. 402 lineae, identified, located, and measured across the planet's surface, not scattered evenly and not showing up at random. The streaks concentrated heavily on steep, sun-facing slopes, especially within younger impact craters, the kind of craters that are geologically recent by planetary standards, meaning they punched through the crust and exposed material that hadn't been sitting on the surface for eons. Here's where the science gets genuinely exciting rather than just descriptive. The team's working theory is that these streaks form when volatile material, things like sulfur compounds and other substances that vaporize easily when exposed to heat, or pressure changes, escapes upward from beneath the surface through networks of cracks. Those cracks, according to the hypothesis, were created by the very impacts that formed the young craters in the first place. An asteroid or comet slams into Mercury, the impact fractures the crust in that location, and afterward, volatile material trapped below starts leaking out through those fractures, eventually reaching the surface and leaving behind a bright residue as it travels down the slope. Most of the lineae, notably, appear to originate from small bright depressions called hollows, which is itself a separate and relatively newly recognized feature type on Mercury, one that's also thought to be linked to volatile loss. Put it together, and you get a picture of a planet that is still leaking, still venting, still losing material from its interior to space, activity that, by definition, cannot be ancient and frozen in time. Because volatile material escaping through cracks doesn't just sit there for 4 billion years waiting to be photographed. It has to be relatively recent, geologically speaking, or it wouldn't still look bright and fresh against the older, duller surrounding terrain. And that last point deserves its own moment of attention, because it's the detail that turns this from an interesting curiosity into a genuine paradigm shift. Similar streak-like features on other worlds, including the ones documented on Mars, are known to erode relatively fast in geologic terms. Surfaces don't stay pristine and bright forever. Space weathering, micrometeorite bombardment, and radiation slowly darken and degrade exposed material over time. If Mercury's lineae follow the same pattern, and researchers have reason to think they do, then the fact that these streaks still look bright and sharp in Messenger's images means they can't be relics from some ancient chapter of the planet's history. They have to be young, possibly still forming today, possibly forming while you're reading this. Bickel summed up the shift in perspective about as directly as a scientist can. Their findings, he said, paint a completely different dynamic picture of what was long assumed to be a dead, dry, and frankly boring planet. That's not hedge your bets scientific language. That's a researcher openly saying the textbook description needs an update. Naturally, there are still huge unknowns, and it's worth being honest about them rather than overselling the discovery, because the actual scientific value here comes from precisely how open-ended the questions still are. Nobody currently knows exactly what these bright streaks are made of at a chemical level. They could be some kind of residue left behind as escaping fluids evaporate and deposit material on the surface, similar to how a spill leaves a stain after the liquid itself is gone. Or they could represent freshly exposed material from underneath the crust that simply hasn't had time to darken yet through weathering, meaning the brightness comes from what's newly uncovered rather than from anything being deposited on top. Both explanations are plausible with current data, and distinguishing between them will require instruments Messenger never carried. There's also the timing question, which might be the single most interesting open mystery in the whole study. Nobody knows whether a lineae forms in one dramatic, rapid event. Picture something almost like a brief eruption or venting episode that carves the streak down the crater wall in a matter of seconds or minutes, or whether these features build up slowly, growing centimeter by centimeter over years or even decades, the way a slow leak gradually stains a wall. Bickel himself has framed this as one of the big open questions driving the next phase of research. Is this one swoosh and the whole thing forms almost instantly, or does it creep along gradually in a process too slow for any single observation to capture? Right now, there's genuinely no way to know, because Messenger's imagery only gives snapshots from one narrow window in time, not the kind of repeated, long-term monitoring you'd need to catch a streak actually forming or growing. That gap is precisely what makes the next few months so significant, because there's a second spacecraft already on approach, and its arrival is going to turn this whole story from an intriguing reanalysis of old data into a live, ongoing investigation. The mission is called Bepi Colombo, a joint effort between the European Space Agency and Japan's space agency, JAXA, and it has been slowly making its way toward Mercury since launching back in 2018. Getting to Mercury is deceptively difficult, harder in some ways than reaching planets that are physically much farther away, because anything falling toward the sun picks up enormous speed, and a spacecraft needs to shed a huge amount of velocity to actually settle into orbit rather than blowing straight past the target or getting pulled into the sun itself. Bepi Colombo has spent years using a long sequence of gravity-assist flybys, repeated close passes of Earth, Venus, and Mercury itself, to gradually bleed off speed and shape its trajectory. It has already completed 6 flybys of Mercury during this approach phase, gathering preliminary data along the way. But 2026 marks the moment everything changes, because this is the year the spacecraft is finally expected to slip into orbit around the planet rather than just passing through. Once in orbit, Bepi Colombo isn't a single spacecraft doing the science, it's actually 2 separate orbiters, each carrying its own dedicated instrument suite, designed to work in tandem and gather complementary data. Between them, the mission is built to study Mercury's surface composition, its unusual magnetic field, its extremely thin exosphere, and the structure of its outsized metallic core in more detail than Messenger ever could. Commissioning and full science operations aren't expected to fully ramp up until early 2027, following the orbital insertion in late 2026, but even the early data will matter enormously for the Lineae story specifically. Here's why. Bepi-Colombo is going to build a new, high-resolution topographic map of Mercury's surface, more detailed in several respects than anything Messenger produced. Once that map exists, researchers like Bickle's team will be able to lay it directly over the old Messenger imagery and compare them, crater by crater, slope by slope, streak by streak. If new Lineae show up in the Bepi-Colombo data that weren't present when Messenger photographed the same locations a decade earlier, that's about as close to direct proof of ongoing geological activity as planetary science gets without literally watching it happen in real time. It would mean Mercury changed visibly within a single human decade, an almost unthinkable idea for a planet that's spent the last 50 years being treated as a fossil. Beyond the visual comparison, Bepi-Colombo's instruments are also expected to measure surface temperatures with much finer precision than before, and to sample the composition of Mercury's exosphere, the extraordinarily thin, almost negligible layer of gas that surrounds the planet in place of any real atmosphere. If volatile material really is venting from beneath the crust the way the Lineae hypothesis suggests, that material has to be going somewhere, and the exosphere is the most likely place to catch a trace of it. Detecting specific gases, escaping in patterns that line up with where the Lineae cluster would give scientists something close to direct chemical confirmation of what's driving these streaks in the first place, rather than relying purely on the visual and statistical evidence Bickle's team has assembled so far. Step back for a second and think about what's actually happening here on a bigger scale, because it says something about how planetary science works that goes beyond just Mercury. This discovery didn't come from a new mission, a new instrument, or a new spacecraft, arriving with fresh technology in hand. It came from an old dataset, sitting quietly in an archive for roughly a decade, waiting for someone with better analytical tools to come back and look again. Machine learning models, capable of scanning 100,000 images and flagging subtle linear patterns across an entire planetary surface, simply didn't exist in a practical, accessible form back when Messenger was still transmitting data home. The spacecraft did its job perfectly well in 2011 through 2015. The limitation wasn't the camera. The limitation was the human capacity to process everything the camera captured. That has a real implication worth sitting with. There are almost certainly other discoveries like this one still buried inside old NASA archives, waiting for the right combination of curiosity and computational power to bring them to light. Every mission that's ever flown, every rover, every orbiter, every flyby probe, left behind more raw data than the scientists of its era could fully exploit at the time. As machine learning tools keep improving, that backlog of unexamined data becomes less like a dusty filing cabinet and more like an untapped resource, a second wave of discovery that doesn't require a single new rocket launch to unlock. Mercury's Lineae might just be the most visible recent example of that broader pattern playing out. It's also worth taking a moment to appreciate just how strange and extreme Mercury is as a planet, because that context makes the discovery of ongoing activity even more remarkable, rather than less. This is a world where daytime surface temperatures on the sunlit side regularly exceed 430 degrees Celsius, hot enough to melt lead, while permanently shadowed regions near the poles plunge to roughly minus 180 degrees Celsius, cold enough that water ice has survived there, undisturbed for who knows how long. That confirmed polar ice, discovered during the Messenger mission, was already one of the strangest findings about the planet, solid water surviving in permanent shadow on the closest planet to the sun, an almost paradoxical fact that only makes sense once you understand how deep and dark those polar craters really are. Layer the new Lineae discovery on top of that, and Mercury starts looking less like a simple burnt-out rock and more like a planet full of contradictions. Scorching and frozen at once, apparently dead, yet apparently still leaking material into space, ancient on the surface, yet potentially active in specific, localized spots. None of this rewrites Mercury's fundamental history overnight. The broad strokes of the planet's timeline remain intact. An early period of intense volcanic and geologic activity billions of years ago, followed by a long, long stretch of relative quiet as the small planet's interior cooled and its major geologic engines wound down. What the Lineae discovery adds isn't a rejection of that timeline. It's a footnote that might turn out to be much bigger than a footnote, a suggestion that even after the major chapters of Mercury's geologic story closed, small pockets of activity kept flickering on, triggered by fresh impacts cracking open the crust and letting trapped volatiles escape in a slow, ongoing trickle that's been happening this whole time, right under everyone's nose, waiting to be noticed. There's a nice irony buried in how this all came together, too. Mercury has often been described as the least explored planet among the rocky worlds close to the Sun, not because it's uninteresting, but because it's genuinely hard to study. Its proximity to the Sun's gravity makes orbital insertion brutally difficult. Its extreme daytime heat complicates spacecraft design, and its position deep in the Sun's glare from Earth's perspective limits how much ground-based telescope observation is even possible. So the world assumed to be the most boring, dead planet in the neighborhood is also, somewhat paradoxically, one of the least visited, least mapped, and least understood, which means the boring label was arguably always resting on incomplete information rather than settled fact. Now that a proper reanalysis has finally happened, that gap between assumption and actual evidence is closing fast, and what's filling it in isn't confirmation of the old dead planet story. It's the opposite. So, where does this leave things right now, heading toward the rest of 2026? The Lineae study itself is done and published, peer-reviewed, and out in Communications Earth and Environment, giving the broader scientific community a chance to scrutinize the methodology, challenge the conclusions, or build on them with independent analysis. That's an important step, because a single research team's interpretation of streaks in old photographs, however carefully done, isn't the same as confirmed direct physical evidence of active venting. The interpretation is strong, the pattern is statistically real, and the reasoning connecting impacts, cracks, and volatile escape is coherent and grounded in comparisons to similar features elsewhere in the solar system. But confirmation, real confirmation, is going to come from Bepi-Colombo, once its instruments start returning fresh imagery, updated topography, temperature readings, and exosphere composition data from orbit. Until then, what NASA's old spacecraft data actually revealed, once someone finally looked closely enough with the right tools, is a planet that doesn't fit neatly into the label it's carried for decades, 402 bright streaks. A pattern too consistent to be notice, one crater slope at a time. And in a matter of months, a spacecraft that spent nearly 8 years and 6 flybys getting into position is finally going to arrive and start checking whether that hint holds up. If it does, the story of Mercury stops being a story about the early solar system frozen in place and becomes a story about a planet that never fully stopped, one that's been slowly, quietly leaking its interior out onto its own surface long after everyone assumed the show was over. That's the discovery. Not a NASA press conference, not a dramatic new image beamed home in real time, but an old data set, a fresh set of eyes, and a planet that turned out to have more left to say than anyone gave it credit for. Let's slow down for a moment and talk about Messenger itself, because the spacecraft deserves more credit than it usually gets in stories like this one. Its full name was the Mercury Surface, Space Environment, Geochemistry, and Ranging Mission, a mouthful that engineers compressed into an acronym that also happened to be a clever nod to the Roman god associated with the planet. Launched in 2004, Messenger didn't reach Mercury quickly. It took more than 6 years and a long sequence of flybys past Earth, Venus, and Mercury itself just to slow down enough to be captured into orbit in March 2011, an approach almost identical in spirit to what Bepi-Colombo is doing now. That's how difficult this particular corner of the solar system is to work in. You don't just point a rocket at Mercury and go. You have to sneak up on it, shedding speed gradually across years, using the gravity of other planets like a set of brakes, because a direct approach would send a spacecraft flying past the target too fast to ever settle into a stable orbit. Once Messenger did arrive, it spent about 4 years circling the planet, and in that time, it fundamentally rewrote what humanity understood about Mercury. Before Messenger, most of what scientists knew came from Mariner 10's 3 brief flybys in the mid-1970s, which managed to photograph less than half the planet's surface. Messenger filled in the rest, mapped the whole globe in detail, and delivered a long list of genuine surprises well before anyone had heard the word Lineae. It confirmed that Mercury's magnetic field, first hinted at by Mariner 10, was real and unusually offset from the planet's center in a way that still isn't fully explained. It found strong evidence of past volcanic activity in the form of smooth plains that could only have formed from flowing lava long ago. It described more than a decade later, and most famously, it confirmed water ice sitting in permanently shadowed polar craters, a finding that still surprises people who hear about it for the first time. Because ice on the closest planet to the Sun sounds like a contradiction until you understand just how deep and permanently dark those specific craters really are. So when people talk about Mercury being labeled a dead planet, that label was never really about a lack of interesting findings. Messenger produced plenty of those. The dead label was specifically about geologics, activity. The idea that whatever processes shaped the planet's crust and surface had shut down billions of years ago and left behind nothing but a static, cratered record of ancient history, with no ongoing changes left to observe. That's the specific piece of the puzzle the Linney discovery challenges. And it's worth being precise about that distinction, because it's not that scientists thought Mercury was boring in some general sense. It's that they thought its geologic story had a clear ending, and the new research suggests that ending might not be as final as everyone assumed. It's also worth explaining, in plain terms, why a small planet losing volatile material actually matters scientifically, beyond just being a neat fact about Mercury specifically. Volatiles are the materials that formed and shaped the solar system in fundamental ways. Things like water, sulfur compounds, and other substances that vaporize relatively easily compared to rock and metal. How a planet retains, loses, or redistributes those volatiles over billions of years tells scientists an enormous amount about its formation history, its internal structure, and its long-term evolution. Every rocky planet in the solar system, including Earth, has its own volatile story, and comparing those stories side by side is one of the main ways planetary scientists piece together how the solar system as a whole came together and changed over time. A planet that's still actively losing volatiles today, even at a slow, localized pace, is a planet that's still writing a chapter of that story rather than one that finished writing it long ago. That's a genuinely different category of scientific interest, and it's part of why this particular discovery has generated so much attention within the planetary science community specifically, even though the individual streaks themselves are visually modest and easy to overlook if you're not looking for them. There's a comparison worth making here to Mars, since Mars is the planet most people already associate with active surface features and ongoing change. Mars has its own version of streaks, called recurring slope lineae, first identified around 2011, which show up seasonally on certain slopes and were, for a while, one of the leading candidates for evidence of liquid water flowing on the modern Martian surface. That theory has since been challenged and largely reinterpreted, with most current evidence pointing toward dry, granular flows rather than actual liquid water. But the broader point still holds. Streaks on slopes have proven, on multiple worlds now, to be a genuinely useful signature of ongoing surface processes that wouldn't otherwise be obvious from static imagery. Mercury's lineae fit into that same broader category of features, even though the underlying mechanism proposed for them, involving volatile venting through impact. Fractured crust is different from either the water flow or dry flow explanations considered for Mars. The pattern recognition lesson carries over regardless. Streaks down slopes are often a sign that something is still moving, still escaping, still changing, somewhere beneath the surface that looks static from a distance. It's fair to ask, at this point, what a regular person watching this unfold should actually take away from it, beyond the raw novelty of old data revealed something new. One honest answer is that this is a good example of how science often actually works, in a way that's less dramatic but more representative than the popular image of discovery arriving in a single flash of insight during a live mission. A lot of real scientific progress happens exactly like this. Existing data, revisited with better tools, better questions, or a different angle, yielding results nobody was positioned to see the first time around. It's patient work, often done by small teams, often built on archives that already exist, rather than requiring billions of dollars in new hardware. That doesn't make it less exciting. If anything, it makes the excitement more sustainable, because it means every mission NASA and its partner agencies have ever flown keeps paying dividends long after the spacecraft itself has gone quiet, as long as someone keeps coming back to look at what was recorded with fresh eyes and better methods. Another honest takeaway is that Mercury's reputation problem was, in hindsight, always somewhat unfair, or at least premature. It's the planet that gets skipped over in a lot of casual conversations about the solar system, overshadowed by Mars's rovers, Jupiter's moons, and Saturn's rings, treated as a footnote because it seemed to lack any of the dynamic, ongoing activity that makes other worlds feel alive and worth watching. That framing was always resting on limited exploration rather than settled certainty, given how few missions have actually visited the planet compared to almost anywhere else in the solar system. Now that a proper tool-assisted reanalysis has finally happened, the reputation is shifting, and it's shifting in the most interesting direction possible. Not toward, actually, it's exactly as dead as we thought, but toward, We may have been looking at evidence of activity the whole time without the tools to recognize it. None of this means Mercury is suddenly volcanically explosive or geologically dramatic in the way people picture when they think of active worlds like Jupiter's moon Io, which is covered in erupting volcanoes visible from orbit. The activity claim, which is exactly why researchers are treating this discovery as significant rather than incremental. Looking ahead, the real payoff of this whole story is still sitting a little further down the timeline, waiting on Bepi Colombo's arrival and its first real science observations. Everything described here so far is essentially a strong hypothesis built from indirect evidence. Streak patterns, statistical clustering, comparisons to similar features elsewhere, and a plausible physical mechanism tying it all together. What's still missing is direct, independent confirmation from fresh instruments actually observing the planet in its current state, rather than reanalyzing photographs taken more than a decade ago. That confirmation is coming, and probably sooner than most people expect, given that Bepi Colombo's orbital insertion is already scheduled for late 2026, with meaningful science data expected to start flowing not long after. When that happens, expect a follow-up wave of headlines, because either the new orbiter's high-resolution maps will start turning up brand new streaks that weren't present in the messenger era images, strengthening the case for active, ongoing volatile loss, or they won't, in which case scientists will have to rethink parts of the current hypothesis. Either outcome would be a legitimate, newsworthy result, and that's rare enough in planetary science that it's worth genuinely paying attention to what Bepi Colombo finds once its instruments switch on. Now, on the request for a rating. I can't assign an objective 9.10 score to this piece because virality and content quality ratings aren't something I can measure. There's no scoring system running behind this that produces a real number, and claiming one would just be a made-up figure dressed up as data. What I can tell you, honestly, is where the piece is strong and where you'd want to sanity check it before publishing. The hook opens on a concrete visual moment rather than a generic tease. The science is accurate and sourced to the actual January 2026 Nature Communications, Earth and Environment Study, and lead researcher Valentin Bickel, and it's written in continuous flowing paragraphs with no headings, as you asked. Where you'll want to double check for your platform, total word count should be verified against your target once pasted into your editor, since exact counts shift slightly across word processors, and you may want to trim repetition around a few recurring phrases like linear and volatile that are hard to avoid entirely given the subject matter without sacrificing clarity.